Well, we ended our last discussion talking about how the chemical environment can affect chemical shifts. And we saw that having electronegative atoms, for example, on a carbon de-shields those neighboring protons and makes them more open to the magnetic field and has a result of a shift towards the downfilled part of our NMR spectrum. Now, one thing that we need to look at is this, is that those shifts, or those peaks that you see, actually turn into characteristic sets of peaks. So the single peak that you'd expect to see, right, from looking at an NMR sometimes can be split into interesting patterns, and those patterns tell us a lot about the chemical environment of that atom. So it turns out here that the signal from a given proton is going to be split by the effect of magnetic fields associated with the protons on adjacent carbons. So this is kind of tricky, and we're going to spend a little time talking about this during this lecture. Now this occurs because there's a small interaction. Sometimes we say that there's a coupling between the two groups of protons. Right now, so we're going to talk more about that too. And the result of that is that there's characteristic peak patterns. So that's really important. There's characteristic peak patterns. So soon we're going to be able to look at an NMR and say, aha, that looks like it must be a methyl group. So that's important because it tells us something about the structure, of course. The other thing to point out is that the signal splitting, the splitting pattern thing that we're going to talk about, does not occur between equivalent protons. So if you have, for example, just the H's of a CH3, there's 3 H's there, but those H's are not going to affect each other because they're chemically equivalent. So it only occurs, again, when protons have different chemical shifts. Okay, now, the intensity of the peaks follows Pascal's triangle. It's probably been a while since we've seen Pascal's triangle. The way that you make this is that you start off here, and we can kind of build one ourselves. You start off with 1s going down your edges. So then that's your second row. So then our third row is this. And the way we get this guy in the middle is we add 1 and 1. So that gives us 2. You get a 1 out here and a 1 out here. 1 and 2 is 3. 1 and 2 is 3. Right, that gives you 1. That gives you a 4. That gives you 6. A 4 and a 1. So on and so forth, right? Now that's the peak intensity. So when we have just one peak, we call that a singlet. So here's a doublet. Notice the doublet has an intensity of 1 to 1. The peak heights are the same right here, right? They're the same height. So if there's the singlet, that's the doublet. Coming over here, you got a triplet. The triplet has a 1. If you look at this, right? It's a 1 to 2 to 1 ratio. So 1 to 2 to 1. That means that the center peak should be twice as high as our shoulders. Right, now as you go on and look here too, here's your quartet. Quartet is a 1 to 3 to 3 to 1 ratio, and then, right, etc. As you get down here to a quintet and a sextet, that becomes a little bit harder to measure out, but still the pattern follows what you'd see for Pascal's triangle. Now there's a convenient rule that we use to explain this. It's called the n+1 rule. And it's also going to help us understand this idea of this adjacent proton phenomena causing splitting. We'll take a moment here and take a look at this diagram. This will hopefully help us understand the n+1 rule a little bit better and how the local magnetic environment can affect our chemical splitting that we see on the NMR. The molecule that I want to look at here below is this. And I first want to point out that if we weren't considering any neighboring hydrogens, that this signal would show up right here. That's the chemical shift of HB without considering what's going on with the proton that's over here at position C, right, well, where that carbon is. So we have this applied magnetic field that's operating and moving in this direction. And remember, when we apply that magnetic field, we get a distribution of spins in the H atom's nucleus, right? The protons. There's some spin in the direction that complements the external magnetic field, and others spin in a direction that really would subtract away from the external magnetic field. So what happens is that magnetic field strength, as that makes its way through and it hits this direction, which is our subtracting direction, right, for our magnetic field, makes its way in, and it comes and encounters in the nucleus of these HBs. When it does that, the B, right, the effective magnetic field that's in here is actually a little bit lower because we've subtracted out a little bit of it right here. And that lower B causes us to have a lower frequency. Lower frequencies, remember, show up on this side of our NMR spectrum. So we see a slight shift upfield there. The opposite's true on the other side. So as we come in with our magnetic field here, we get a boost. Right? And as we go in and hit inside of our nucleus of these two guys, we have an increase in our effective magnetic field that's inside those nuclei, and that causes a higher frequency and a higher resonance frequency. So we see a shift slightly downfield. So there's a slightly upfield shift and a downfield shift. And so these protons, these HB protons here, are going to get split into two peaks. The way that n+1 rule works is we look over here at our neighbors. N is equal to 1. So n+1 is equal to 2. And that's why we see that. That's described as a doublet. Now, last thing, the distance between these peaks is something that's important. We talk about that a little bit more in second semester, but that distance is called the coupling constant.